but
no.
no, let's be serious. They wouldn't. No. All right, whatever. Now, before I get to the problem I talked about at the very beginning, area of a polygon, there's another example that's interesting to take a look at, because it shows how certain things that you have to be careful about when it comes to working with these vector fields.
So I imagine you can apply this same thing to a volume pretty readily too, right?
There is a three-dimensional version of Green's theorem, and we're going to sort of work our way up to that. It's like one of the very last things we'll see.
Yeah, that's fine.
Yeah. Okay. Now, here's a vector field. Minus y over x squared plus y squared, x over x squared plus y squared. Now, this is actually equal to the gradient of little f, where little f of xy is the arctangent of y over x. Where has this come up before, this function, arctangent of y over x? What? Polar coordinates, yes. Yes, how you get theta in the case where x is positive. All right. So we say, oh, this is conservative. Okay. But then, suppose you take a circle around the origin. Radius doesn't matter. The point is it's centered at the origin. So, if I think, well, this is conservative, therefore, if we look at the line integral over some curve, like this curve C1 is the top half of the circle, or C2, which is the bottom half, you might expect these to be equal, because that's what a conservative vector field means, that its line integral is path independent. However, that's not the case. The line integral over this piece is equal to pi. Line integral over this piece. So we're going from this point to this point. You actually get minus pi.
Why did you draw the arrow in the clockwise direction?
Because the idea is I want to have the same initial point, same terminal point. Because if the integral is path independent, if we're going from same initial to same terminal, the value of the integral should be the same.
Right.
No matter what path we take, but we end up getting different values, that it's pi here and minus pi here. So on the surface, it looks like a contradiction. That we have this vector field that is conservative, but it's not path independent. Well, it turns out this is not a contradiction at all. Can anyone think why? If you look at this particular vector field,
wouldn't it just be because of the direction you're traveling? Like last time, when we had our greatest value is I guess the smaller value is the.
Oh, I see.
We had to switch the sign, but since we're not traveling counterclockwise, we're traveling where the region's to our right. It's the opposite direction. So wouldn't we have to flip the sign?
Well, that is what's causing a flip of sign in this case. But the thing is, if it's a conservative vector field,
okay,
it should still work out.
Can we take another path, like right along the axis?
Well, it turns out if you take whatever paths from this point to this point, you're going to get different values.
Right.
So, but this is not a contradiction. What is wrong with this vector field that could cause everything to fall apart? This whole chain of reasoning that, oh, it's a gradient, big F is a gradient of little f. Therefore, it's a conservative vector field, should be path independent. But there's a flaw.
Well,
If you look at the original functions themselves, the answer lies there.
Good divide by zero error?
Yes, not defined at the origin. It's got to be, so big F has to be gradient of little f, everywhere in the region that's being enclosed. It fails at this one and only one point, and that brings everything to a screeching halt.
Oh my
Hey,
God.
that's math. In math, as in life, little details will get you.
So if you move that whole thing up to where the origin's not in there, then it all works out.
Yes.
But that's because then it's all positive, so then it'd be pi.
Whatever value you get the same value from point A to point B, whatever that value would happen to be. So in that case, everything's fine.
That's kind of cool.
And there's something else you can get from this, though, that's also cool, is the following. Now, let's define this region. We take any ever closed curve, we orient it properly, and then we'll orient the circle properly as well. So now what we have is a region with a hole in it. So now the origin is not included in this region. Well, this region satisfies the conditions for Green's theorem. So what you get is that the integral of whatever vector field, including this vector field, so these are functions p and q, is equal to the double integral of qx minus py dA. But what do we know about these partial derivatives when the vector field PQ is conservative? That came up last time. How did we check whether a vector field was conservative? What's the simple test for that?
I remember the joke you made.
These partial derivatives have to be equal. Yes. Yes, I'm sure, and I'm hoping you would have found it if you noticed if you kept looking. Okay. All right. So that means this whole thing is 0. So what that means is, the boundary of this region D includes both curves. So what that means is that the integral over the first curve, I'll call this, I'm already using letter C, so it's called C1 prime, that's the outer boundary. Is equal to the boundary over this curve, the entire circle, which I'll call C2 prime. If we give both curves this orientation, so counterclockwise for this one, counterclockwise for this one, because the integral over C1 prime with this orientation and C2 prime with this orientation, you add those two together and you get 0. That's what this is saying. But now, if I switch the orientation of this one, so that now serving as a boundary of a disk, that means that the line integrals over these two pieces, C1 prime, C2 prime, are actually equal. But this integral, I know what this is. This is a disk. And I can pick it to be an appropriate radius, something that fits within this entire region. And it turns out that no matter what radius I pick, if I evaluate the integral, which I do in the notes, you get 2 pi. So what that means is the line integral of this vector field over any closed curve that contains the origin is 2 pi. I don't even know what this curve is. It doesn't matter. but because